Log on, tune in, find out. Another good idea from Cambridge.
Sergey Foss from Harriet Watts, and I just want to introduce you.
Okay,
Blackboards, I think.
Okay. Yes, so I would like to do something more, so I would say ancient style talk. So I would like to introduce, yes, two models, related models, and the second model we agreed that Andrew Richards will help me. Yeah, it will be so it may create some discussion and so on. That's what may be the reason for this talk. And thanks for planning my talk at the end. So, okay, thanks to Stan for the introduction, and I will speak about models with buffering and original. So the setup is close to what did Stan introduce, but then I will deviate from his model. So what do we have? We have the demand, and there is a conventional supply plus wind supply. They depend on time. We may include some reserve in demand, but in any case, we have to assume that this should be the case. So in general, the demand and supply are varying, and I'm speaking, so it's in the nationwide level. So yes, at this level, as we agreed, so demand is understood, predicted, and may be known. And yes, in addition, I would like to have some buffer. And and what I would like to consider, I would like to consider the models in the first model. I would like to control buffer size and wind. Yes, farms. And the second model, in the first model, to control buffers and wind when demand and conventional supply are given. And in the second model, I would like to look at the supply, conventional supply, and it's more uncertainty with the second model, and we will discuss it later. So I will start with the first model. And so what do we see? So the first model where demand and supply are given. So I will just, if they are given, if I cannot do anything about this, I will denote this by d hat, say of t. It's given, and for simplicity we may assume it's just a constant. It doesn't matter. And we assume that wind, W of t, is just a sum of k sources, and I will use it small wi of t, and we assume the sources to be identical. One can do this as follows. Yes, assume they're identical, and there are there are many options. Yes, how do they behave? Does their behavior correlate or not? So the simplest scenario is that these are IID random variables, or the other extreme is that there are copies of each other, and there. Yes, and because yes, the first one may be realized, and these are wind farms which are located in different regions, and the wind speed differs in these regions. The other one is completely opposite, when there is a small place where all these wind farms are given, are located, and therefore either they all work together or not, or they produce some level of speed, and so level of speed, a level of energy, so that's the same level. So anyway, So, and what is the omega I of t? Dennis said that we like indicator functions. For example, we may assume that omega I of t are indicator functions. And yes, omega I of t is just indicator functions. The simplest scenario is that of this form. You may have, if you have speed between say 5 and 25 miles per hour, you may have something like this, or you may have something like this. It doesn't matter. So it's yes, either this or this. Yes, the story. So and depends on the wind. Whatever. So first of all, I will assume that situation A1, 1A. So again, W of t is given, and we assume that we have, as Stan described already, the extra buffer, and so we may have the following scenarios. So of course we have to assume that both are possible. That what might be possible? That d may be bigger than W, and d may be smaller than W. To make the situation reasonable because of variability of W. And so what I may draw the following, yes, and I will introduce the buffer, and the buffer or storage is a buffer, and the storage level is just s of t, s of 0 plus integral from 0 to t, say r of u du, where r of t is Stan, yes, I just using different notation, but essentially what this Stan says. So there is a maximal buffer level. Level is m. Zero, and r of t equals to W of t minus d, a constant, if s of t is between 0 and m, equals to minimum of 0 and W of t minus d if s of t is at the top, and equals to maximum of 0 and W of t minus z if s of t is at the bottom. So exactly what, sorry, it should be r of t here. And this is exactly what this Stan says. So it's a very simple, very simple scenario. So we just we cannot the m cannot be the total content of a buffer cannot be above level m. And this is the rate how does it increase or decrease. One can change this. One can assume that there is a. You can change a little this definition. One may assume that buffer size. So the R of buffer content may leak, energy may disappear, whatever. But it's I don't want to consider this at the moment. And the question is now it's just what did I say up to now? It's just almost repetition of what did Stan say. But now look, what do we want to optimize? We assume that we have to pay some price for storaging, for store the energy. And so in particular, so we may think that we may have the following rate of to pay. So we have the following function. So we can take a function L of t. I would like to average it 1 over t, and take integral from 0 to t, to t, of 3 components. I would say C1 s of t, if s of t is s of u, if s of u is between 0 and m. plus C2 indicated that S of u equals 0 plus C3 indicated that S of u equals m du. And so this is what I would like to consider a linear cost of this form. So each unit of energy we have, we have each unit of energy, and we want to, so we have to pay for its storage, yeah. We may assume that, so this C2 means the following: if the buffer content is empty, and it means that we have to borrow electricity from, say, from French connection, and so it becomes much more expensive. C2 is much bigger than everything else, and C3 may be equal to C1, C1 times m. But you may say, you may say, we pay for storage, for storing the energy, but we also pay for something for getting rid of the extra energy. So C3 is usually, it is at least C1 times m, but maybe something big. And so the idea is we have this function. We may assume for large t, we may assume this model to be stable or not, or whatever. And if the model is stable, then when t tends to infinity, this converges in a proper sense to some limit, or we may and we may analyze that limit, or we may fix some time t and try to analyze this in the average, whatever, or we may take expectation if one likes, and to analyze this aggregate. And clearly, so you see that if C2 is sufficiently large and C3 is bigger than C1, then the question is here in this particular model to find M optimal. To find M optimal, and this is the model I would yes, the model which is of interest to me, and so I would like to I just started formulate this model to so introduce this model to one of my PhD students, and he is supposed to write a program and to do this numerically, some optimization of this type of model. I would be happy to get critics on that model and to some comments on that. That's it. In addition to that, so any questions? It's a very simple linear model. Of course, there is a big variation of this stuff. Yes, you may consider non-linear cost, whatever, but only in the linear cost we can do something. You know, there is a chance also to get some analytical result. It's clear that if the cost is not linear, there is no any chance to get optimality analytically, and you have to do some numerical stuff. So, yeah. So this is the story, and of course, one can also one can just instead of this, you also can introduce some aging procedure like discount price, like E minus T, like yes, discount, because it means this type of discount. Yes, energy may disappear. You cannot yes complete for it, and you also can do E minus alpha T here, put here, and then it's also it becomes more interesting. So the first model of this type is one-dimensional, maybe multi-dimensional. So this is what I want to. Yes. Yeah, okay. In addition to that, I would like to say that we are all, no, at least I myself. So it's I'm a reader. I'm writer. I'm not reader, mostly. But there exists a story. We are trying to introduce new models, but something of this exists, of this type. And I would like to say that thanks to Ona Boxma, I looked at yes, there is some existing literature in this direction, and So I learned, thanks to Anna Boxman, I learned about that literature. And for example, there are some papers, like a paper by Schneihardt. One for Forest and Mandius. And it's 2005. And there's a paper, and yes, and there are papers, and there is papers by Boxma with co-authors. It's 2005 and 6, and so I can give references more precisely. They consider the following particular model. They assume that there is a discrete version of that. They assume that the storage level S of t may take only values. Sorry. They assume that okay, maybe start again. They assume the following scenario. Again, so each wind farm may be either on or off. Each one. So a very simple scenario. Each wind farm is only on and off. The W's are either so Wi's of t are either W or say 1 or 0. And this is the second story, which relates to I would say AB. Now we want to control the W of t. I was not precise. Okay. Precise. So this is the story how to take M optimal. But the second one is how to control WT. And so this is the story which relates to these models. So each of farms may be on and off, and each of farms are in the same at the same level. So they assume that there is a given numbers. There is a given numbers on Wj. Now say Wj a given numbers. W1 smaller than W2. Say W1 is 0. W2. Say W. They call it WF. These are levels, and each wind farm which is on, it produces this level of energy simultaneous at the same time, and and it's off. It produces 0 level, 0 units of energy, and more generally, one may consider the following situation. That situation is if the S of t is between some interval Li and Li plus 1, where Li are given numbers, increasing numbers, and then they use the following policy. If S of t is between Li and Li plus 1, and if the wind is in state J, then say they use the following policy. They say f of I j farms are on. So this is the model which was produced. So there is a k on-off farms which behave completely in the same manner, and they use the following model, and they found some analytic or numerical results in this particular case. But this relates to this in this discrete setting and doesn't relate to continuous space. Whatever. So that's all about the first model, and I would say about the second model just few words. And the second model is of this type. It's more basic. Now I cannot control anything, and it's not I, but we cannot control anything. We cannot control wind. We cannot control buffer. Forget about buffer. It's outside. It's something like that. But we want to control how to control conventional. How to control the conventional demand. And this is a classical situation of this type. Yes, we have this is okay, and this is I would say I would do it as follows: put it downstairs. So this is the difference. I would like to consider difference between demand and total supply minus C of t minus W of t. And we have the following story. So what do we have? We have the following story. At each time t, we have a prediction, some function, up to time t plus 4. I count everything is hours. And this is a given. This is a given deterministic curve. And then the real scenario, yes, what happens? It's a random curve around it up to this time. So we observe the demand, which we observe this forecast. We have forecast up to t plus 4, and we have the real observation up to time t. And assume we have the following. We have, for simplicity, two types of conventional supply. The first type of conventional supply is cheap, but you have but in order for it to be switch on, you need 4 hours. Say again, so Andrew said, for simplicity, we assume if you decide at this time that we are very close to 0 difference, it's be a dangerous situation. We may decide, let's switch on this supply in advance. And the second idea, a second supply is expensive, but it's say almost immediate. So if we decide to if we decide to switch in advance to switch on the demand cheap supply, and it occurs that the wind is blowing up, and so we go up. We lost some money, and because we cannot switch it off immediately, but we can do nothing, and essentially, so and then we can do nothing, and we may achieve we may arrive at the boundary. Then you have to pay a lot of money to have the inequality of demand to add something to compensate this negative difference. And so the question is how to simulate, how to model this randomness around. So we have the real situation. So denote this white line is x of t, and this is y of t. So and so y of t is clearly x of x of x of t. It depends how to say. So x of t plus epsilon of t if you use the same time, or you can use the change. So we have this is in this notation x of t plus 4, yeah, this notation. And so the question is how to model this epsilon and what to do with that. I'm sorry I spent more time than they expected. Yeah, and there are several ways how to do it, either using whatever. So I'm not certain how to do this model. So maybe Andrew, maybe it's the right time to comment. You have something.
The idea behind the model was that when in control times, what you do is you've got a demand forecast, you add reserve onto it, and the control engineers are trying to make sure that they've got enough generation to be above the demand plus the reserve. So to all intents and purposes, you can take that demand forecast plus the reserve as a deterministic level. Stan and David earlier sort of referred to the variability of the wind, and Stan said the wind was essentially unpredictable. But we can predict it to a certain extent in that we have forecasts. What we don't know is exactly how accurate those forecasts are going to be. Griffith was dealing with the wind as a time series and trying to get the right types of properties into his time series that would reflect the wind. And my sort of idea was that the wind forecast, if it's a good wind forecast based on meteorological principles, should have essentially the same sorts of properties as the actual wind will. It'll have the right type of properties. It just won't be entirely accurate. And in the equation that Sergei has written there, the y of t is the actual wind, x of t is the forecast, and epsilon of t is the error in the forecast. And somehow the error in the forecast ought to be something which is easier to get hold of than the actual behaviour of the wind itself. So if we knew what sort of situations we had, suppose we knew that the forecast was reasonably constant, and we had some sort of idea of how epsilon t behaved, we would know that with a constant forecast, the best thing to do for 4 hours' time, if we could see that there was a shortfall in generation, might be to say, okay, we're reasonably confident about what is going to happen. Let's fire up a generator that takes 4 hours to warm up before we can use it, and we'll use that in the future. But if we were in a situation where the forecast had a rapid ramp, and we were aware of the fact that we didn't know exactly when that ramp was going to happen, it might actually be better for us to wait until the ramp came and then use the expensive but quick firing generation. And what I was hoping to be able to do was to say, by looking at different cases in the shape of the forecast that we've got, and having some understanding of what the error is, we could use the forecast to decide our control policy of whether or not we were going to meet the shortfall in generation by using the cheap generation or the expensive generation or some mixture of the two. That's essentially the idea behind the model.
Mm-hmm. And so what the possibilities are? So we may assume we may have something like Brown motion around.
I've done a little bit of analysis into the error,
yeah.
And it looks to me like one of the things we might be able to do is model the error between the wind forecast and the actual outturn as an autoregressive process of sort of order 4. It does turn out to be that. I was looking at a time series with 1 hour steps, and an AR4 model with normal errors seemed to fit several of the weather stations that I looked at. So that's one possibility. Another possibility I thought of, which again reflects something I said earlier this morning, is that you tend to, with certain weather systems, you tend to get a certain level of variability. When a new weather system comes along, the level of variability you've got changes. So again, it's some sort of Markov model where the variance is at one level for an exponential holding time, and then you get a transition into a new weather state where the variance might increase or decrease. So some sort of underlying Markov model driving the variance process seems to me a possibility.
How do wind prediction errors compare? So, if one type is wind persistence, wind prediction, and meteorological, on the time scale more than 1 hour.
David knows more about the wind errors than I do.
Yeah, there's been some recent analysis, and in what I call short time scales, 12 hours and 24 hours ahead, during periods of calm conditions, easier to forecast, our errors get down to about 7%, which is pretty good. But on the same kind of time scales, with stormy conditions, the average error over the months that we've done the analysis over, get up to about 18%. And the analysis has been done for the last 10 months. So it's been strongly influenced by the weather that we've experienced in December and January, which was extremely stormy. Further ahead, say 3 days, 4 days, the errors tend to get worse the further ahead as I said in my presentation, we were attempting to forecast all the way up to 10 days in advance for trading purposes and for organising reserves and managing the system.
And persistence is good in some situations.
Well, it's ideal.
But not in
totally
others.
repeats all the characteristics of the wind.
If your forecasts are telling you that there's a big ramp coming, then persistence isn't a very good idea. I think Stan did some work on this sort of thing, and you had some sort of autoregressive model for wind, didn't you?
Yes, just treating as a time series. But not different from yours. I settled for autoregressive of order 3, but 3, 4 units, neither here nor there.
Well, 3 and 4 were the two numbers that came out of the error process.
Yeah.
AR4 was slightly better than AR3, but only did.
Mm-hmm. Okay, that's it. Thanks. So thank you, Andrew. So just before we finish, so I would say both to finish again. So both models were influenced by my discussions with Andrew Richards, and the first model with my discussion with Ona Boxma. And so yes, I would like so that the first model to proceed with the first model with one of my PhD students, and with the second one, the second PhD.
Well, there's some more general questions before we end? More specific.
Okay.
So can I just ask about that on-off wind farm? So do I understand it right that there's a finite set of values for the wind farms to choose
Yes.
from?
So we yes.
And if storage is within,
We have this. So in this particular case, R of U equals to Fij times W J
what is Fij?
farms upon Fij farms upon. So this is a rule. You introduce a function f of ij. So it says the following: if s of t is
I measures the level of storage.
So you measure the level of storage. I put the numbers numbers L1, L2, so Li, Li plus 1. If S of t is here,
I and J.
if S of t is there, and the wind speed is omega j, then Fij farms are 1.
And it's a policy.
It's a policy. It's a policy. It's your decision. So it's a.
I think perhaps we should thank Stan especially, and also the Newton Institute for the hospitality today, but for Stan for organising today's arts workshop.
Newton Institute did all the hard work.
Absolutely.